started. So we'll start on chapter 5. So the exam again, Mu'in has a class until 5:30. I did not know. So and I will be at Rasgas until maybe 2:30 or 3. So I think 5:30 would be the exam. Mu'in prefers actually room 217 instead of 037. So I will update that and send an email. Yeah. So is that okay with everybody? Not 037, not the lab. 217. I think it's one of the electronics lab or the 214 lab or something like that. He says the desks there are much nicer and
Next Wednesday, right?
Yeah, next Wednesday. Okay, that's until the end of chapter 4 material. Yeah. Okay. Okay, so we'll get started on chapter 5, the AC voltage controllers. You'll find this very, common sense based on what we've done before. So again, in this chapter, we'll cover single-phase versions, three-phase versions, and then some applications. Yeah. So this is an example of an AC to AC converter. So remember what we covered so far was the AC to DC converters. Yeah. So the rectifiers. So now we'll do the AC to AC type converters, and there are many ways to do this. There's you can take an AC converted to DC like we did, and then take DC converted to AC again, which is something we will do with chapter 8. That's the inverters. We will not do it this way. In this chapter we will cover direct AC to AC conversion using power converters. Yeah. So it's very commonly used in induction motor speed control. Not really induction motor speed control. Induction motor starting. Starting of induction motors is something that is highly dependent on what that stuff we talk about here, and also the application of or integration of power electronics directly in the utility is also dependent considerably on something like that. So for example, we talked about if you add capacitance to a power system, right? That will change the power factor angle. Remember, the power factor angle is dependent on the angle between voltage and current. So the angle between voltage and current depends on the impedance of the system. So the impedance of the system, if it's more inductive, if it's lagging, it's a lagging power factor. If it's more capacitive, it's a leading power factor. We said that the utility doesn't want to put in too much reactive power because it's not something they get paid for. So they typically want to limit power factor to a certain level, right? So to do that, if the system is highly inductive, what would you do? Add some capacitance. Right? It's highly inductive, so the current is highly lagging. So if you add some capacitances in different places in the system, and how do you locate these capacitances and stuff? That depends on how much reactive power. Again, if a portion of the power system is drawing too much reactive power, that's where you want to locate the capacitors. I mean, not in a place where loads are not consuming a lot of reactive power. So placing these capacitors is a different issue, right? So we don't discuss that. But how do you placing these capacitors in the power system can be done using simply a capacitor and a switch. Yes, whenever the reactive or power factor is too low or lagging too much, there's too much lagging power factor, or meaning too much reactive power being pumped in the system, you add some capacitors, and then whenever you see the power factor needs correction, you switch them on, turn the capacitor, switch the capacitor into the system. Fine, that works fine. Again, we don't want to operate this power system in leading power factor. As you will see in 459 later, if you operate the power system in leading power factor, you're actually limiting the capability of the generators to send power. Okay, so that's something we will derive in 459, and we'll talk about in 459. But for now, power system or generators in the power system like to operate in lagging power factor. How much lagging power factor? That's up to you. That's up to the utility, really. But I mean, again, you don't want to. Again, the generator will provide a certain amount of apparent power, right? So active and reactive power. So if the power factor is lagging significantly, then you're providing a lot of reactive power, which means you're limiting the amount of active power, right? So it's apparent power that's important, right? So if you're not being paid for that reactive power, then you're not going to be able to compensate your investment because you're not charging enough real power because you're not generating enough real power, right? So you always want to operate in lagging mode to not limit the generator's capability to provide power. Okay, so that's one constraint. The other constraint is the amount of reactive power is something that will also limit the amount of real power that you can sell, because the generator is rated for a certain amount of apparent power, right? So the utilities like to regulate power factor. They don't do that on individuals. They do that on big industrial facilities or big consumers. Yeah. Okay. So they tell them operate at this is your worst power factor, can be 0.9, cannot be worse than that, right? So that's an example. Yeah. So instead of just putting capacitors in the system using just a simple switch, because this has some drawbacks. What are the drawbacks of just, you have a power system or a voltage source or a line, a transmission line, and you just connect a capacitor to it? What's going to happen to the current that will be drawn out of that power system? What will it look like? You connect a discharge capacitor across the line. What's going to happen? Yeah, not pure exponential. Remember, current across the capacitor changes instantaneously, right? So current will, you will see these spikes of current that we saw before when we were talking about the rectifiers, right? So you will see huge spikes in current. Again, if you put a sinusoidal voltage, you will instantaneously want to see a cosinusoidal current. So whatever you are in the sine wave, you're going to jump up and meet that, have the corresponding value for cosine at that point, right? So it's going to be a big jump or a big spike in current to be able to charge that capacitor. Why? Because again, you're changing the dV by dt, right? IC, the capacitor current, is equal to C dVc by dt. Capacitor was not charged. Voltage was 0. Now all of a sudden you want to change the slope of the voltage, right? So IC equals C dVc by dt. So now all of a sudden, meaning in a very short period of time, you've instantaneously put the switch on, trying to force this capacitor voltage to be equal to the line voltage. So there's a huge slope change in the C dVc by dt. Like the dV by dt is changing very quickly in a very short period of time, meaning the current will be this spike, right? So that's something we don't like. You can live with it, for small size capacitors, very distributed, etc. But let's say you're at a big industrial facility like Rasgas or Qatar Steel or whatever, right? And you have these capacitor banks. These capacitor banks, if you're going to be switching them on and off, because you don't want to put too much capacitance at some point and then operate in a leading power factor, right? You want to make sure you're always lagging. So sometimes when you're consuming lots of reactive power, you bring in lots of capacitance into the system. Then you switch them out when reactive power consumption goes down. So you've turned off the motors, you've turned off the transformers, right? You've disconnected these inductively reactive power consuming loads. Yeah. So these turning on and turning off of capacitors will cause these inrush currents. So it's something you don't want because they will cause harmonics. These harmonics can interact and ruin your other equipment, or can ruin your voltage profile, meaning if you ruin your voltage profile, maybe your protection system will trip, and maybe these high spikes in current will be detected by your protection system. It will trip because you have very sensitive loads that you've set your protection system to protect. There are other reasons to do that. So instead of these switches, the manual switches, we can use power electronics. If you use power electronics, you don't need to switch the full capacitance in and out, right? Remember, we have an SCR, right? With an SCR, I can only put for example, I can put a small portion of the input voltage across my load and keep increasing that. So I can increase that and decrease that. I don't need to switch the full bank of capacitors in and out, right? It's called bank of capacitors. Capacitor banks, that's what they're called. It's the terminology that we use, yeah. So you can slowly apply a voltage to the capacitance and slowly remove it, meaning you can slowly add reactive power and slowly remove it. So it's a nice dynamic change of reactive power versus a sudden switch on, switch off application here. So that's the static VAR controller, and we will talk more about that. Induction motors are very similar. If you took 338, for example, or even if you hadn't, induction motors are basically like a transformer, right? So it's like a rotating transformer from an equivalent circuit perspective. We said that if the transformer has this time-varying MMF, then it will develop the back EMF voltage across its winding, which will limit the current that's coming in, right? If you apply a current across a winding, just a piece of wire, take a voltage source, apply a current or a voltage source across a piece of wire, what's going to happen? You will have a huge amount of current. right? If you take, it's a short circuit, basically. But if this piece of wire is wrapped around the core, for example, and this core has time-varying flux going through it, then there will be a voltage developed across that piece of wire that's wrapped around the core. That voltage developed, if you've properly chosen the number of turns, can equal the amount of voltage that you're putting in, for example, right? Or you can have a small difference. If you have a small difference in the voltage, then you will push current, right? That's basically the idea. If you have this voltage difference, then you will be able to push the current through the transformer. Induction motors are the same thing. So it will develop this back EMF voltage when it rotates, when the motor rotates. So initially, the motor does not have the back EMF to stop the inrush of current, right? But then when the machine rotates, it will develop this back EMF, simply speaking. So that means that initially, as soon as you put the three-phase supply voltage across an induction motor, what will happen? You will have a huge amount of current initially, and then the current will go to steady state. To be proportional to the torque constant to the output torque, for example. Okay, so that's how induction motor works. So this will also benefit from the same thing we were talking about. If I'm able to slowly apply voltage across the motor, I'm not going to apply full voltage across the motor, because we said if I apply full voltage across the motor, it does not have a back EMF to block this current from flowing, so it looks like this short circuit at the beginning. Simplistically speaking, like the transformer case. But as soon as it starts turning, it will develop a back EMF voltage like the transformer across its windings. Okay, so as soon as it starts turning. So what does that mean? That means if I now apply a small voltage, not full voltage across the motor's terminals at starting, then I will not get this huge inrush current because I'm applying a small voltage across a short circuit initially, for example, right? And then what's going to happen? This will rotate the motor a little bit. Then some back EMF will develop, so I increase the voltage, and so on and so forth. So I'm able to start my motor, but I don't have this huge inrush current. And I get that benefit if I'm able to apply the voltage slowly across the motor's terminals. Of course, the problem with that is, as you've probably studied in 338, is what? Induction motors do not like you to change the terminal voltage only without changing the frequency, right? So for induction motors to produce torque, rated torque, you're supposed to change the V over F, the voltage, maintain the voltage over the frequency ratio constant, right? So because the voltage over the frequency is what's proportional to the flux in the air gap, which is what's going to produce torque, right? So induction motor control, or starting of induction motors using this AC voltage controller technique works, but it will not work in applications where you need starting torque. If your load, for example, if you have an application where you're lifting something, okay, you have a lift. If you have a lift, you have load from t equals 0, right? From at speed of 0, you have a load to lift, right? But if you have a pump application, a centrifugal pump, centrifugal pumps' torque speed characteristics look like something like this. Something like this. So this would be torque, and this would be speed for a centrifugal pump. In this case, I don't have torque at 0 speed. There's no flow. I'm not pumping any fluid. And then when I turn the pump, I'm slowly pushing into the fluid into the pump, and I'm raising the torque. The torque is going higher as the higher the speed I go. I'm pumping more. There's more torque that's required to pump more at that point. So in this application, a motor that has low starting torque will be okay, right? But in an application where you have a lift that requires a certain T minimum torque to start the lifting process, this motor's torque speed curve will not work. You have to have a motor's torque speed curve that is above this point, right? If this is the torque speed curve of the motor, these are two different motors, or the same motor but started two different ways, for example, right? If I'm using this application of gradual application of voltage, then I'm not maintaining V over F ratio constant, meaning I cannot operate the motor at max torque anytime. If you're able to operate motors with V over F constant, then you can control torque easily in the motor. And you do that, and this can be done with what we will study in chapter 8, which is inverters, power PWM inverters. We will study how we can change voltage and frequency. But in the AC voltage controllers chapter, we will study only how we can change voltage that we apply. And if we change voltage only, it's nice, we can do it. And it's actually the workhorse of the motor starting industry. The motor starting industry highly depends on what we're going to talk about in this chapter. But it's great for a certain kinds of applications, not any application. Okay, so that's something I wanted to note here. Also, the other application of this is light dimming. Light dimming, these incandescent lamps, for example, they're resistors. I don't care. The resistor does not really care what waveform you apply to it to produce power, right? It will apply the output power from that, which is proportional to the light intensity, for example, is I squared R. This is the power consumed by a resistor, right? It's I RMS squared times the resistance, right? So as long as I'm changing the value of the RMS current, then I can control the intensity of the light, right? Does not really matter what the waveform really looks like, if it's highly distorted or not. I just want an RMS value of current, right? So these are three very big applications of these AC voltage controllers. The light dimming industry, the motor starting industry, and the reactive power industry, reactive power integration to the power grid industry, right? So these are the three big applications of what we're going to study here. And we're going to look at the circuits, the corresponding circuits that help us do that. And of course, you can do this in single phase and three phase. Okay, so we will study both cases. Yeah. So I just said that we just discussed the main applications, and we'll talk about them in more detail. I think by solid state relay, I think relays are mechanical contacts, right? So mechanical contacts that connect a load to the AC or source or disconnect it, right? So I can do that with a thyristor. Right, so instead of using a mechanical contact, I can do this with thyristors, for example. So that it's and in that case, I'm also applying a certain amount of the AC voltage to the load, or a certain amount of time. For example, I'm applying voltage for a certain amount of time. So this is the two types of control that are discussed here are phase control and integral cycle control. I can change the amount of RMS value by doing two types of control. I can either, for example, if this is my input sine wave, I can take a portion of it and apply it. Oops. I can take a part of it and apply it to my load. And this way I would have changed what? The RMS value. I can change the RMS value of current or voltage applied to the load, right? That's called phase control. Phase control, meaning you are changing the firing angle of the thyristor. You're changing the phase of the firing angle of the thyristor. That's called phase control. You can also change this RMS value by doing something else. It's called integral cycle control, meaning, let's say I have, 10 cycles. This is my input voltage. If I do this, if I have a way to, chop these down into 2-cycle intervals, right? And I connect the thyristor here, and I disconnect it here, connect it here, and I disconnect it here, connect it here, disconnect it here. Right? I connect my load during these intervals, and I disconnect them during these intervals, right? If I calculate the RMS value, I have to look at my period. My period now is this, right? This is my full period. Right? In this period, I am connecting for a while, disconnecting for a while, connecting for a while, disconnecting for a while. What did I do? I change the RMS value as well, right? So I can change the RMS value this way as well, yeah. So this is called integral cycle control. The other is called phase control. Certain loads, this will work. Certain loads, this will work, right? So for a motor, this can work because the motor has inertia and stuff like that. So you can probably apply something like this to it, yeah. Whether we want to do that or not depends on the size of the motor. For example, if it's a very large motor, I don't think you want to do that. Because for a very large motors, you probably, just for the first 2 cycles, the current will be very high. You will lose the benefit of what I was talking about, trying to apply a small voltage to the motor so that the starting current will be very low. In that case, it's better to use phase angle control and just, within the whole initial sine wave, only turn on the thyristors in these parts. Right? Provide an alpha here and an alpha here. That way, you're only applying a very small amount of voltage to the motor's windings initially. And then you move alpha back. So alpha will change from you can change it from 180 degrees all the way to 0. After you change it to 0, finish, you've put in all the voltage across the motor. And the motor was designed for this 50 hertz and this full voltage. Then the motor can provide full torque at that moment. At that time, the motor can provide full torque. Right? But initially, the starting torque will not be the motor's rated starting torque because you've applied a small voltage, but you've not decreased the frequency. If you would have decreased the frequency as well, then you can still apply the full torque, right? And that's what we do with inverters, plus with modulated inverters. You can change voltage and frequency. With these, you cannot. But there are many applications where you don't want a big inverter. You don't want a big power PWM inverter. You want a simple AC voltage controller like what we have in this chapter. Okay, so do you see the different applications? I hope. Okay. So, simply speaking, this will be the first type of controller we will discuss. Let's draw the corresponding waveforms. So we have an AC voltage source here, and I will have a thyristor here, and I will have a thyristor looking in the opposite direction, and I will have my resistive load here. So, and this is my output voltage. If this is my input voltage, what does V output look like? The way I would control this thyristor is as follows. In the first half cycle, I would provide a gating signal to thyristor 1. Because if I provide a gating signal to, okay, let's forget about these being thyristors. If they are diodes, and this is 1 and this is 2, okay, what would the output voltage look like if they are diodes? Exactly. The output voltage will look exactly the same as the input if they are diodes, okay? So remember what we said about thyristors. For thyristors, the delay angle is from where the diode would have conducted, correct? From where the diode would have conducted. So the diodes now are conducting from here, right? We agree? So that's where I'm going to start my delay angle alpha, right? So now I will add the delay angle alpha. In the first half cycle, I will add the delay angle alpha, and I will provide the firing signal to thyristor 1 here. This is to device 1. And then in the negative half cycle, so in the positive half cycle, I don't provide anything to thyristor 2. I mean, it's looking in the opposite direction anyway. As a diode, it wouldn't have conducted. So then in the negative half cycle, I provide the gating signal to thyristor 2 somewhere here, right? So now what will my output voltage look like? Yes. Mm-hmm. Yeah. Yes. Okay. How about current? Exactly the same because it's a resistive load. Now, how about if I change this to okay? Do we see that do we see now that of course I've been able to control the RMS value of voltage or not? I mean, I've only put a portion of the waveform onto my load, applied it onto my load. So if I want to calculate RMS, V output RMS, it's equal to what? Right? If alpha is the same in both cases, so to calculate the RMS value, it's 1 over the period. The period can be only pi, right? Because this is the same value, and the RMS will, I'm squaring the waveform, so I have the waveform. RMS. I'm squaring it first, so it means negative or positive doesn't really matter, right? So then I can do it only across over a period of pi. So 1 over the period, integration of what? The waveform, which has the equation of Vmax sine omega t, for example, in this case. Vmax sine omega t dt, right? From where? From alpha, sorry. This would be your firing angle alpha, from alpha until pi, and then this would be squared, right? So I squared the waveform. I found its mean value, so 1 over the period, integration over the period, and then I've placed everything under the square root. Right, so that's the RMS value. So obviously the RMS value will depend on alpha. So if we look at, I think the other waveforms here that they show, okay, so here they show the input voltage, and then the output voltage and output current look identical, right? That's like we just drew. And of course, if this is the output voltage, right, then what's the voltage across the switches? When the switches are on, the voltage across them is 0, right? So obviously this is 0, right? When the switches are on, output voltage is 0, here and here. When the switches are off, if these are off, meaning from this node to this node, it's like an open circuit. So what does V switch equal? This is open circuit. There's no current flowing. That means the V switch is equal to V input, right? So that's why the V switch looks like V input at the beginning until alpha. Okay? So that's these waveforms. So this is something we called an SCR. We also called it a thyristor, right? When you package two of these together, especially for low power applications, you cannot find this in a high power application. When you package these together for lower power applications, it's called a triac. They actually sell the package like that, two together like that. It's called a triac. Okay, so but it's nothing but two thyristors inside the same package here. And because they know these applications, applications for AC voltage control require these two thyristors back to back in a back-to-back connection here, right? So it's a very common application. So industry has developed devices for people to buy that include both devices together. Okay, so now the natural extension to that is RL, right? So how will that affect the waveforms? Let's see. So instead of my R only, I have a source, back-to-back thyristors, or my triac, and then I have an R L type load. What does V output look like for this input voltage? This is V input. I want V output. And obviously we should know by now that it's always important in RL type circuits to draw the current. Right? I hope we know that by now. And I will provide firing angles similar to before. Provide firing angles here for device 1, device 2. Okay, so what does the output voltage look like? And what does the output current look like? Always think of the process, right? Resistive load. For the resistive load, what did the output voltage look like? It looked like 0 initially. And then when I provide the thyristor signal for thyristor 1, it looks like a diode now. If it's acting and behaving like a diode, what will it do? It will conduct, right? It has a load here, there's a source here with a positive voltage here, right? So it will conduct current. So thyristor 1 will conduct, meaning the input voltage and the output voltage will look the same, right? Until here, it's like the resistive load case, right? And then what happens?
Follows depending on how big your conductor.
Exactly. Then we have to look at the current waveform, right? So we don't know where we will stop. We have to look at the current waveform. So the current waveform, what will the current waveform do? Here I have an RL load. I have connected my source to my load. So what's going to happen? Exactly. Same shape of waveform for current as we had before. exact same shape, and the equation for the current will be exactly the same, right? In this case, however, instead of, remember, for the half-wave rectifier, the waveform for current looked like this, right? And then, in the second half cycle, there was no voltage, so it was 0. And then another one of these, right? That was the half-wave rectifier. So for the full-wave rectifier, it was a continuous current. Remember, as soon as we had full-wave RL case, it was continuous current, right? So for the half-wave, we had this. We had current waveforms that look like this. And here we will have exactly the same shape waveforms. Because I'm applying the same thing. Here I'm applying, now I'm taking my sinusoidal voltage, I'm applying it to my output. So I have a current that's going to ramp up, and it will not fall here, because this is where the resistive load current will become 0. It will fall somewhere beyond. Somewhere beyond will be the extinction angle. Exact same theory, actually exact same equation for current. Does not change. There will be the I of t will be composed of a natural response and a forced response. The natural response is AE to the minus t over tau. The forced response is the voltage divided by the impedance. Vmax sine omega t divided by the impedance. And so you'll end up with exactly the same equation than before. That equation has the constant A. This A is determined from initial conditions. Exact same, the exact equation doesn't change actually. It's the same equation that we had before for the half-wave rectifier. Okay, so now what? Now what does the output voltage look like? So now that I know that this stops here, what does the output voltage look like?
Keeps going negative.
Keeps going negative until here, and then stops here. It's fine. Now I provided a thyristor gate signal here. So what happens?
That's all.
Hmm?
The other.
No, it cuts off. Thyristor 1 stops here. It
Yeah.
commutates here, right? And then I provided a gate signal for thyristor 2 here in the negative half cycle. So thyristor 2 will look like a diode, and now, as soon as I provided the gate signal, it looked like a diode. Where? Starting from here, right? And then it will continue all the way until here if it was a resistive load. If it's not a resistive load, it will stop where? Where the current stops. So here I have to go down to the current. Draw the current waveform, right? It would have stopped here if it was a resistive load. If it's not a resistive load, it will continue. I can go back here, and because I'm drawing one cycle, I flip over, right? I start over again. So it will start here. The extinction angle will be somewhere here. So the waveform will look like this. Yes, you're confused? Why? How?
The second half cycle, the second firing angle, the current shouldn't it be negative?
The current, yes, you're right. Sorry. I should be negative. Sorry, I automatically drew this. Good point. So yes, the current will look exactly the same but negative. I apologize. I agree. Thank you for pointing it out. Yeah, unlike the half-wave rectifier, where the voltage was positive, right? In the next half-wave, I was still applying positive voltage, same polarity. Now it's not. It's going actually through this thyristor, so it's negative, right? So, good point. Thank you. Everybody's okay with this now? Okay. So this is the R and RL. There's no RL in a source in this case. I don't think so, at least. And this is the equation for RMS. And then again, you will have this final equation for you, but you should know how to calculate RMS value for any waveform, right? Like the waveform that's in the exam, it's a simple square wave. RMS value is something easy to calculate because it's areas under the curves, right? You can easily calculate areas under a square or a rectangle or a triangle. So the integration will be easy because it's flat, integration of 5 squared. It's a constant, right? So if I give you something, it's not going to be complicated, but it's going to be testing your ability to apply the theory that we understand that we studied in class. I'm not quizzing you on your ability to integrate and use the cosine rule and all the trigonometric relationships that I don't cover in class, right? So I would not give you a difficult integration. I would give you a problem that requires you to go through and demonstrate that you're able to do an integration like this, but on a simple scale, like the DC, a rectangular wave, or a triangular wave, or something like that, right? I would not ask you to do something with a sine wave or a cosine sine with two harmonics or something that's too complicated. Here they do this output voltage, so they take this curve and they draw it graphically for you. So they represent. Obviously, we know that if we increase alpha, we keep decreasing the amount of voltage that we're applying, and that's what they show here. So you can increase alpha until you've brought the voltage down all the way to 0. So this is 180 degrees. Okay. So, and then you keep decreasing it until you apply the full load, as we said we want. So any questions on this? Obviously, these are not nice output sine waves, right? This is not a sine wave. The output voltage and the output currents are not sinusoidal, right? They are at 50 hertz or at 60 hertz, whatever the input frequency is. Do you agree? They're repeating at a frequency equal to the frequency of repetition of the supply voltage, which if it's at 50 or 60 hertz, then they are repeating at 50 or 60 hertz. So now think of this relationship between waveform shape and Fourier spectrum, right? If I have a waveform that's repeating every 50 hertz, right? And this waveform obviously has no average value, right? The area on top is equal to the area on the bottom, right? So what do I expect the spectrum, the Fourier spectrum, to look like? Definitely no average value, because the area on top is equal to the area on the bottom, right? Area on top is equal to area on the bottom. So no DC value, no DC component, right? And then what do I expect to see? I expect to see a significant component at 50 or 60 hertz, which is equal to the input fundamental frequency. I expect to see that. And then I have these huge jumps, right? These huge jumps indicate a spectrum of other components, lots of other components as well, right? So that's what. But are they significant compared to the 50, 60 hertz component? No, the area under the curve for the waveform that's occurring at 50, 60 hertz is considerably large. I mean, it's considerably larger. It will have significantly more effect. There will be much more power in that spectrum by just looking at the waveform, right? An impulse function is different. The impulse function is a very small function, right? So it doesn't have infinite amount of energy. It's a very small amount of energy at many, many frequencies. So it's like having an impulse function here, and then a waveform at 50 or 60 hertz here, right? So that's what you should expect, right? You should expect something that looks like that from the output spectrum here. Yes.
So if we have a low-pass filter for that circuit,
Yeah.
what would the output look like?
If you have a low-pass filter, the low-pass filter will not allow this quick jump, right? So it will make it look like, you know, it will rise slowly. So depending on how sharp your low-pass filter is, then you will eliminate some of the high frequencies. How much of the high frequencies? Are you eliminating, everything beyond the 5th, or everything beyond the 7th, or everything beyond the 100th? That depends on how sharp your filter the filter bandwidth is, right? So if your filter looks like this, it's very different than a filter looking like this, right? This filter would definitely allow more harmonic content, right? So it will allow, maybe a a sharper rise in the waveform like we have here. Not the same thing, but because you have a filter, but at least it will allow a sharper rise than this one, for example. This one is eliminating anything beyond 50 hertz, for example. Here, the output would look like a pure sine wave, for example, right? Because there's no average value, and this is something that's eliminating everything beyond 60 hertz. Ideally, this is not, doing something like this would be a very high order filter, for example. In this case, I would only get a sine wave, pure sine wave. You only get the fundamental, right? You'll only get the fundamental in this case, because this is the harmonic content. So at every delay angle, let's say I put a delay angle of 40 degrees. For a delay angle of 40 degrees, here I have a huge amount of fundamental, big, nice fundamental sine wave. And then I have, some 3rd, 5th, 7th components. They're not small. I mean, it's when at a delay angle of 50 degrees or so, they're 20% of the fundamentals. So they are. You will see them. You will not see a nice pure sine wave yet. But if you put a nice ideal filter, yes, you will only see this one. Right. So this is a graphical representation of the Fourier series of this waveform as well. Right. Cn is the Fourier component. The Fourier series component that we talked about in chapter 2. So any questions on this? So we agree there will be some harmonic content with this application. Yeah. This is the RL case that we discussed. The waveform I didn't do, of course. The output voltage waveform, we went through that. Obviously, when there is no output voltage, right? If there is no output voltage because there is no output current, that means this switch is an open circuit. If it's an open circuit, then the voltage across the switch is equal to the voltage across the supply, like the previous case, and that's what you see here. Okay? Clear? Everybody's happy with this? Again, the equation for current is exact. If you go back to the half-wave rectifier current waveform, it's exactly the same. This is the forced response, V maximum sine omega t, divided by the impedance, and the impedance, this is the magnitude, and they brought the angle up here, right? And then this is the AE to the minus t over tau, just phase shifted by the alpha. Okay, so it's exactly the same equation as the half-wave rectifier current waveform equation. And the extinction angle, and same thing, the extinction angle is something we have to find numerically. You cannot, there's no closed form solution. It's the same process like the half-wave rectifier extinction angle calculation. Okay, so that being said, that's good. So now we do three-phase. Any questions on the single-phase one? So three-phase, this would be more interesting because there will be lots of coloring here. So let's first think of the diode case, okay? Let's first think of the diode case. If all these are diodes, what is the output voltage across phase A? Exactly. Right? Remember our three-phase discussion, right? This is if all these are diodes, it's like putting wires, right? It's like putting wires here, and then these are three balanced loads. If these are three balanced loads, I can connect this neutral here, and no current will actually flow. So I can actually take this point and connect it to this point. So now I have phase A circuit looking like this, right? So that means that across phase A load, I have phase A voltage. Across phase B load, I have phase B voltage. Across phase C load, I have phase C voltage, right? So that's the case for all diodes. So now if I look at thyristors, where will my alpha start? It will start from where the phase voltage equals 0. Do we agree? Because the output voltage on the phase is equal to the phase voltage. So any delays will affect the output voltage on the phase, which had, in the diode case, would have started from 0 of the phase voltage. So that's where my alpha will start. Okay? So let's draw that. Okay, the other thing is, okay, so now we agree that if all of them are on, then I have phase voltage A across load A. How about if I have, S1 on and S6 on? What is the phase voltage across phase A? Exactly, it's VAB, that's fine. But, or I can say what? If A and B, if VAB, if VA and VB are equal and phase shifted by 120 degrees, right? Then I have VAB voltage source. So I put this line voltage here across what? Across these two resistors, right? S1 is on and S6 is on, right? So this VAB voltage is applied where? Across these two resistors. So it's VAB divided by 2, right? So VAB divided by 2 is what's applied here or here, right? When S1 and S6 are on. Similarly, if S3 and S4 are on, it's not S3 and S4. If I have, how about if I have S3 and S2 on? What's the phase voltage across VA? S3 and S2 are on. What do I have? What do I see across phase A?
A?
Yeah.
Nothing.
Exactly, right? So these are the cases we will have to deal with when I draw the exact waveform, so that's why I want to make sure it's clear. How about, okay, so for a balanced system, if I want to operate, induction motor is a three-phase load, right? If I operate an induction motor unbalanced, then there are consequences of that the motor will heat up, the motor will not be able to produce enough torque, and that's because of something. Okay, so if you have, I mean, in 459 we will study what's called symmetrical components. Symmetrical components are a theory, a mathematical theory that can take three-phase voltages and then chop them up into components. If they are a balanced set of three-phase voltages, if you're applying a balanced set of three-phase voltages, symmetrical components theory does nothing. You put it into a, let's put in, imagine you have your three-phase voltages coming into a box that has your symmetrical components coming out. Symmetrical components are voltage components of different frequencies, okay? So if you put in three-phase balanced voltages, you will get three-phase balanced voltages at the output of that box. That's it, that's all you'll get, right? But if you put three-phase unbalanced voltages in that box, right, you will get three-phase balanced voltages rotating in the same fashion as your input. You will also get three-phase balanced voltages rotating in the opposite fashion. I know we spent a lot of time on this in 459, but basically, if you have three-phase waveforms that are not balanced, then you have the theory that we talked about, the three-phase balanced circuits that we talked about last time, we cannot apply it. Do we agree that the theory last time we discussed on three-phase relies on what? That sources are balanced, equal, and 120 degrees apart, and the loads are balanced and equal. Right? We have, that is the case. Only in this condition can all the stuff we talked about from three-phase perspective apply. But this is not the reality, right? The reality is this room is on, the other room is not. This is a reality. It's a reality. In this case, what's going to happen? In this case, we will have current in the neutral wire if we have this neutral wire connected, right? What is this current? And what is it an indication of? It's an indication of some imbalance happening in the system, right? So imbalance happening in the system is something that we will deal with mathematically in 459. Here, we will not allow it to happen, right? Here, from a control perspective, we will assume that our voltage sources are balanced and our loads are balanced. So now, if I want to operate this system in a balanced fashion, I will have to make sure that whatever current comes in from, let's say, if S1 is on and S3 is on. If S1 is on and S3 are on, current is coming into this node. I have to make sure that I turn on S2 so that the sum of currents into the node equals 0 and I don't have neutral current, right? So let's look at the waveforms. I think when we look at the waveforms, it will be clear here. Let's see. Import. So first thing I want to note here is I have these waveforms, VAN. It's the phase voltage across phase A. Okay. How about, do you see the reasons now why I have here VAB over 2 and VBC over 2 and VCA over 2? Right? Because what I want to draw is I want to draw the output voltage on my load. Right? The output voltage on my load will sometimes be the input phase voltage, which is VAN, right? If I have all three diodes on, in this case, or it will be the line voltage divided by 2 because I've taken my line voltage and then applied it to 2 equal resistors and chopped that in half, right? So that's the reason why I went to that discussion. So that being said, let me do this, okay? So if we go back to the drawing that we have here, if we go back to this waveform here, I have a certain numbering of these thyristors, okay? So this is 1, 4, 3, 6, 5, and 2. So I want to draw. I don't want to draw the whole thing in the next page, but I want to. Okay, the S1 is the device pushing current in the positive direction in phase A. Okay, S4 will be the device pushing current in the negative direction in phase A. And then S3 will be the device pushing positive current in phase B. S6 will be the device pushing current in the negative direction in phase B, and so on and so forth, right? So I will write this in a, instead of drawing the circuit, I will just write S1 phase A positive, S4 phase A negative, because I don't have space to draw on here, because this is one full cycle, and I need to keep one full cycle of the sine wave. Okay, so I will just represent the drawing using this notation. I will say S1, S1, S device 1 will be in phase A, positive. 4 will be phase A, negative, and 3 will be phase B, positive, and 6 will be phase B, negative, and switch 5 will be phase C, positive, and switch 2 will be phase C, negative. Okay, so if you go back to the drawing of the circuit, you will find that this is what the circuit means here. Okay, so now that I have all of these up here, now let's look at my three-phase voltages. My three-phase voltages: VA. This is VA, VB, and VC. These are my three-phase voltages that I'm applying to the circuit. Right? These are my three-phase voltages I'm applying to the circuit. What's going on here? So let's look at, divide this up into portions like we did last time. So let's not here. I'll show you where this is coming from, okay? Very shortly, 1 second, just give me a... Okay, so how did I come up with these? These are 6 zones as well. 1, 2, 3, 4, 5, 6. Okay, these are 6 different zones as well in the full fundamental period of my input. So what's unique about in this zone? In this zone, phase C voltage from the beginning of the zone till the end is positive. Phase A is also positive, right? And then phase B is always negative, right? So if all the devices were diodes, which diodes would be conducting in this zone? All these devices were diodes.
1, 4.
Yeah, 1. You look at phase C, positive, so it's 5, right? Phase C
1, 5,
is positive, so 5, and then phase A, positive, would be 1, right? And then what else? And phase B, negative current will be conducting. And phase B is 6, right? Remember we said that if they're all diodes, then we have a balanced system. It's like wires going through there. Okay, so let's go back to the drawing. Okay, if they're all diodes, it's like just putting wires. If we're just putting wires in there, then the phase voltage is across the phase load. Phase voltage is across the phase load. Phase voltage C is across phase load, right? So if phase voltage C is across the load, I can draw the equivalent circuit outside, like a single phase, AC voltage controller, right? But instead of thyristors, two diodes. Current will only go negative through phase C if it's through diode 2 when the voltage of phase C is negative. And same thing on the other phases, right? That's where this came, how I drew it up came from. So let's go back to what I drew. So hopefully this is now clear why in the diode case, these are the diodes that would have been conducting, because 5, 6, and 1 are corresponding to phase B flowing negative current. Obviously, because I have negative voltage, I have a single, again, remember this is equivalent to exactly putting a half-wave rectifier like circuit, but with an AC source like this, right? If this is phase C, this is phase C voltage and it's in the positive half cycle, only the top diode will conduct in the positive half cycle, placing voltage and current through this resistive load, correct? And that's why here phase C is positive and I go up to phase C positive, then I know that device 5 would be conducting here. Same thing with 5, 6, and 1 for the other phases, okay? So now, how about the rest of the slots? Can somebody help me fill which diodes would have been conducting? If all the devices were diodes, which devices are conducting in this zone?
1,
Not 1, 2, and 3.
1, 6, 2.
Exactly. So it's 6, 1, and 2. How about here?
3, 1,
Yeah.
2.
1, 2, and 3. So you look at the pattern. You're dropping the first one, you're keeping the next two and adding them. So 1, 2, and 3. So 1 drops, 2 and 3 stay, 4 is added, 3 and 4 stay, 5 is added, 4 and 5 stay, 6 is added. But go through it, okay? Please don't. Everybody's okay with these? Okay. So if that's the case, let's see now what's happening. So if these are all conducting, then what is my output voltage across phase A load? I'm only going to draw the output voltage across phase A load. If these are conducting, what is the output voltage across phase A load?
Only when A's are on.
If these are all conducting, if this is what's happening, what is the output voltage across phase A? Remember, this is the old diodes case. The old diodes case is what? If they're all diodes, it's like pieces of wire. It's like a wire here. Then what's the voltage across phase A? VAN. It's the phase voltage of source A. Because if all of these are diodes, meaning all of them look like, all of these combinations of back-to-back diodes look like just wires, right? In that case, I have phase A connected to load A, and then these two neutral points connected. I can draw the equivalent circuit, single phase equivalent circuit outside, right? So if the combination that if the diodes are conducting in this fashion, or the switches are conducting in this fashion, for this whole interval, then I have VAN at the output. VAN on phase A. VAN is this pink waveform. Okay, so that would be the output voltage waveform if these devices were all conducting for the duration of this period. Now, this is not the case. Now we want to do this for an angle of, let's say, delay angle of alpha equal to 30 degrees. Because the objective of this AC voltage controller is to change the voltage applied on the load, right? So now with the diodes, or with all wire case, the phase A load will see phase A voltage. Now I want to change that, control that. I want to be able to control that all the way down to 0, right? By controlling the delay angle. So at the delay angle of 30 degrees, what do I get on the output phase A load? So it's the same logic, right? So that we tried to do last time. Here, which device was turned on here? No, 6 and 1 were on from before,
Yeah.
right? So we turned on 2. So 2 will turn on 30 degrees from where this line is. How about here? Which device was turned on?
Wood.
Device 1 was turned on because 4, 5, and 6 were on. 1 was turned on here. 1 is turned on 30 degrees away from where? Remember we said it's from where the phase voltage was starting. Because if for the all diode case, the output voltage on phase A is equal to the phase A voltage, right? This is the output voltage on phase A. For the all diode case, or the alpha equals 0 case, the output voltage is equal to the phase voltage. So now if I am going to delay, it's the delay with respect to the phase voltage, right? Because these two are the same. So it's, the delay is going to be applied with respect to the phase voltage. Phase voltage starts here. So the delay will be 30 degrees from here. 30 degrees from here, we'll draw these lines. So 30 degrees from here is where these two intersect. I chose 30 degrees because it's easy to draw it here. Okay. But I mean, the idea is the same, but it's easier to draw because of the intersections here. Okay. So this is going to be 30 degrees from where this red line is. I need to do the same thing here. Where is that? It happens to be here. 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 And here. Okay, so these blue lines are 30 degrees away from the red lines. The red lines are where the corresponding diode would have started to conduct. Here 2, here 3, here 4, here 5, here 6. Okay? Yes?
This alpha happens to all the diodes at the same time?
Why are you saying at all the same time? This is happening to alpha. This is happening to SCR 1 here. Nothing else to SCR 2 or 3 or 4 or 5. This is, I'm providing the gate signal to 1 here, providing a gate signal to thyristor 2 here, providing a gate signal to thyristor 3 here, providing a gate signal to thyristor 4, the gate signal to thyristor 5, provide gate signal to thyristor 6. Okay, you get it now? No, you don't, it's not at the same time, because you will simulate it. In one of the homework problems, you will simulate this. So you will, I think you will not like the simulation, but it's a good learning process. You will. This question will be answered then, right? So but now you know that it's not at the same time. Okay, so now what? If I don't turn on 1 until here, okay, what do I have on in this period? Beyond this blue line, which devices are on? For the diode case, 5, 6, and 1 were on here, okay? But now I don't have the diode case. I have all thyristor case. I had turned on 5 and 6 here. 6 started here. In this zone, I know 5 and 6 were on. Okay, so 5 and 6 were on. They continue to be on, right? But is 1 on? 1 is not on until this blue line, right? So from this blue line to here, I know which devices are on. Which are the devices that are on? 5, 6, and 1, right? So 5, 6, and 1 are on here. Okay, which devices are on here then? 5, 6 are on here. You're right, right? Because 4 cannot. I mean, 4 is what? 4 is A negative, right? And here A is positive, right? So A is pushing positive current through, right? So you cannot have the A negative be on you. Okay? So here devices 5 and 6 are on. Here device 5, 6, and 1 are on. How about here? Here 6 and 1 are on. Here 6, 1, 2 are on. Here 1, 2 are on, right? Here 1, 2, and 3. We'll do half cycle. Okay, we'll stop here. You can repeat the next. There's no time. So now, if device 5 and 6 are on, it's the same. After that, it's here. It's what? 2 and 3, and then here 2, 3, and 4, and then 3 and 4, 3, 4, 5, blah, blah, blah. Okay? So now let's see. So if 5, 6 are on, okay? 5, 6 are what? 5 and 6, you go here. 5 is C positive, right? 5 is C positive, and 6 is B negative, right? So what voltage do I see on phase A? 0. Do you agree? And that's why I went to that exercise at the beginning. So here, output voltage will be 0. Now, 5, 6, and 1 are on. What is the output voltage? VAN, exactly. So I jump to this pink line, right? And then 6 and 1 are on. What's the output voltage? Exactly, right? So 6 and 1, I go, 6 is the B negative, and then 1 is the A positive. So it's VAB divided by 2. So this is VAB divided by 2. So I follow this red waveform. The red VAB divided by 2 is the red waveform. So it looks like this. Right? How about 6, 1, and 2? What's the output voltage? VAN. Remember, the same. This is the same as this case. So the output voltage will look equal to phase voltage. And then 1 and 2 are on. 1 is A positive, 2 is C negative. VAC divided by 2. Or A positive and C negative. So VAC divided by 2, right? VAC divided by 2. Because this is CA is the green. Right? So I have to draw CA. Right? So I will take this green and draw CA. You know, some will look like this. Right? Take my blue back again. So this green is the this green dotted line is the VAC divided by 2. So it's going to be VAC divided by 2 in this zone. And then here 1, 2, 3. VAN again. Back to 0. And then you repeat. Okay? So let's look at what it looks like. The class time is over, but let's look. So let's look at what the slides show. The slides show this in the next here. So this is what we just drew, right? And then at 180 degrees goes to 0, and then it repeats again. It repeats in the negative fashion. Okay. So and then they draw the 3 waveforms VAN, the phase A voltage, phase V voltage, phase C voltage. They're exactly the same, but phase shifted by 120 degrees. What did I do here? I changed the value of the RMS value of voltage. I changed the RMS value somehow. Okay, we're not going to even worry about the equations for this because it's not possible to come up with an equation for this. You have to simulate it and look at the area under the curve, and we cannot come up with an equation for this easily. So next time we'll just wrap up this. I mean, the corresponding current will be in the device will be whatever, because the resistive load, so it will look exactly the same as the voltage basically. So we'll wrap this chapter up next time quickly, and we'll start a new chapter. So this chapter is really short, So I hope it was clear. So you will